the amount of charge will deplete. Deplete means decrease within this surface.
Yes.
So in that case, these charges are flowing outside the surface. So this will constitute the current, and that current can be expressed as minus of d by dt. D by dt means rate of flow of q in, minus because it is decreasing within the surface. As the charges are
Yes.
increasing, the rate is decreasing. So this current is d by dt of q in, because q in is coming out now. So it is d by dt of q in, but negative because now it is decreasing. Am I clear?
Yes, sir. Okay. Yes, sir.
So this, so see very carefully this expression. Is it clear to you? I out is equal to integral of j dot ds is equal to minus of d q in by dt. Here the figure is not given. The figure would be something like that. That is, there is a closed surface, charge is there, and charges are coming out of this surface. No doubt?
No, sir.
Now if you see, here again, I would like to ask you j dot ds, for this expression, only for this expression up till here, apply the Gauss divergence theorem. So what you can write?
Mm, surface integral
Apply the Gauss
J dot.
theorem.
Uh, uh, means it will convert it into volume integral.
So what will be the final expression for this one? Just to help,
Uh,
volume is what?
integral del dot J dV.
Yes, over the open volume, right?
Open one. Ah, yes, sir.
So this is what it is written here. Applying the Gauss divergence theorem, that surface integral of j dot ds is del dot j dv, right?
dV. Yes, sir.
Yes. So see, so now you see here, this equation j del dot j dv is equal to now minus of d by dt of q in, because instead of this, I'm writing this. So now this is
Yes, sir.
equal to this. Okay.
Yes, sir.
Now you see, if rho v is the volume charge density, then q is equal to rho v dv.
Yes.
Yes or no?
Yes.
Yes. So instead of q, I am writing rho v dv. So see here very carefully. dq in by dt is minus d by dt of volume integral of rho v dv. Yes.
Yes.
And see, here it is the total differentiation, but now I am writing it as a partial derivative, because rho v may be a function of x, y, z, comma t. Means this is a function of space as well as time. But here
Okay.
we are interested only to differentiate with respect to which quantity?
Time.
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 So the partial derivative. The partial derivative of rho v with respect to time dv over the integral v. Right?
Okay. Yes.
Now I will replace this with this and this with this, because this one is equal to this one and this one is equal to this one. Then j dot ds is equal to this one, and minus of d by dt of q1 is equal to this one. So for this side, for this left hand side, I can replace this equation, and for the right hand, I can replace this equation. Agree or not?
Yes, sir.
Yes. So this is what has been done. So why I am discussing this, this will become, see, very soon it will become much clear. So this is what, as you said, yes sir. So in the last slide, this is what I am writing for that del dot j dv using the Gauss divergence theorem for I dot, sorry, for j dot ds. Yes, yes.
Yes, sir.
And here for
Yes, sir.
minus of d by dt q in, I am writing this one. Already I have explained this.
Hmm. Hmm.
Now you see, left hand side volume integral, right hand side volume integral, dv of course for the volume integral. Then can I write del dot j is equal to this quantity?
Yes.
This is a very important equation. This is known as equation of continuity. Please remember this.
Okay.
Here also it is written continuity of current equation. So this is known as equation of continuity. So what is the equation of continuity is that divergence of the current density is equal to what? The partial derivative of volume charge density.
Volume charge density.
In the mathematical form, in a statement form, I can say that what is actually divergence? Divergence is the outward flux, right? So
Hmm.
the
Hmm.
net current coming out of a surface is equal to the decrease in the volume charge density. And that will be, of course, if it is
Okay.
coming out, charges are coming out, so that will be a decrease in the charge. So the net
Hmm.
current coming out of a surface, closed surface, is equal to the rate of decrease of charge.
Charge. Hmm.
Am I clear?
Yes, sir.
Yes. So be very careful. Then one more important equation which has not been derived here. This we perhaps already we have derived it in the plus 2 level. J is equal to sigma times E. So remember this.
Hmm.
Where sigma is
Hmm.
what?
Conductivity.
Conductivity. So J is
Conduct.
equal to times E. Okay.
Hmm.
And according to Gauss law, del dot E is equal to rho v upon E epsilon.
Ah. Yes, sir.
Yes. Now you see very carefully. J is equal to sigma times E. Del dot E is equal to rho v upon epsilon E. Now what we are actually doing that instead of J, J is sigma times E. So del dot J.
Hmm.
So J
Hmm.
is in place of J I can write sigma E.
Hmm.
Yes.
Yes, sir.
Yes. So I am writing the sigma E and see, once again I go back to the previous slide that del dot E is rho v upon epsilon. If I multiply
Hmm.
sigma both sides, then I can write del dot sigma E is equal to sigma rho v upon epsilon.
Yes.
Am I clear or any ambiguity is there?
No, no.
No. So this is very clear. So this is what I am
Hmm.
writing. Del dot sigma E is equal to sigma rho v upon epsilon, and this is nothing but J. So
Hmm.
I'm having another equation which was something like this. This other equation of continuity which we have derived. Del dot J is equal to minus of del rho v upon del T. Of
Hmm.
course. So this is what I have written here. So this is actually, see, I'm not using the whiteboard, but this is now I hope you understand that how it has been derived.
Yes, sir.
Is it clear?
Yes. Yes, sir.
If any doubt, please ask. Don't say only yes, yes. If any doubt,
Hmm.
be free to ask. That will only help you. Okay. Then here, if you see very carefully this equation, now it is nothing. I have taken this term this side, and I can write this delta of from here to here. If you see from here to here, from here to here, I can write delta rho v upon delta t plus sigma by epsilon rho v is equal to 0. Agree?
Ah, yes, sir.
And this is a linear differential equation. We have studied in the plus 2 the linear differential equation. And there is a method to solve the linear differential equation that is known as variable separable.
Hmm.
Do you remember?
Yes, sir.
So here we have used the variable separable. So I can write delta rho v upon rho v. We take this side
Okay. Hmm.
divided by rho v is equal to minus of sigma by epsilon delta t.
Hmm.
Any doubt?
No, sir.
If you integrate both sides, so what will be the integration of del rho v upon rho v? Let's see.
L and rho v.
Yeah, natural logarithm.
Log.
So
Uh,
and one constant here. So natural log rho v is equal to this. This is a constant. Delta t
hmm.
means delta t integration is t. So sigma by
Hmm.
epsilon is constant. So minus of delta t upon epsilon plus log of rho v naught. That is a constant taken in form of logarithmic constant. Because
Hmm.
I want to express this in a better form, so we have taken it in a
Mm.
logarithmic constant. Okay.
Mm.
So
Yes.
yeah. So then, oh, sorry. Then the expression which I get here is very another very important equation, that rho v is equal to rho v naught times e to the power minus of t upon tr, where tr is the epsilon upon sigma. See, tr, and what is this
Epsilon.
tr? Tr is called as the response time, or sorry, or the relaxation time, not the response time,
Mm.
relaxation time. This TR is called as the relaxation time. So this expression rho v is equal to rho v naught e to the power minus of t by TR. This expression is useful to
Mm.
find the transient response. Have you heard this term, transient response?
Yes.
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 So here, if you put T is equal to TR, if you put in this expression, here in this expression, T, this is small t is equal to TR, then this will be e to the power minus 1. Yes?
When t equal to t. Ah, yes.
E to the power minus 1.
Yes.
Then from there I can get e to the power minus 1 is 1 upon e, and this is approximately 0.368.
368.
If I multiply this by 100, I will get 36.8%. Okay?
Mm.
So here is the another important point, that definition of the relaxation time. You should know that may be helpful in some problem. That relaxation time is the time in which a charged particle in the interior of a material drop to 1 by E, that is 36.8% of its initial value. This is the definition of the,
Okay. Means tau.
sorry,
Is it tau?
2,
Means tau.
tau.
Tau. Tau.
Tau is actually generally the constant RC, but in
Ah.
it is same like that tau.
Okay.
It is same like that
Ah.
tau, but here since there is no RC, so there is to
Ah.
distinguish it, it has been given a separate name TR. That is the relaxation time.
Okay. Ah. Okay.
What you are saying is that tau you have studied in the network theory and control.
Ah. Yes.
Yes, you have studied it.
Yeah.
It's similar to that. One by there also we say that what is the that tau means transient response is the 37% of the initial value, right?
Initial. Yes,
Here
sir.
also it is the same thing, but with the only thing is that scenario has changed. The frame of reference has
Yes.
changed.
Okay.
Okay. There you find the
Ah.
decay. Here also you are finding the decay, but here you are finding the decay of the charge. There you find the
Touch.
damping. There you find how much it is damping. Okay.
Yes.
So if you can recall, as you are preparing for the GET, so you must have studied. So there you are finding
Ah.
the damping, but how fast it is damping. And here you are finding that how fast it is depleting. Okay.
Okay. Mm.
So relaxation time is the time in which a charge placed in the interior of a material drops to approximately 36.8% of its initial value.
Well, mm.
Is it clear?
Yes, sir.
Any doubt you may ask, you may share.
So this initial value, but uh, means what? Uh,
Yeah, okay. I got your
uh,
point. What? It is asking that, let's see, just actually here I didn't go for each and every step derivation. That is why you are asking this
okay.
question. No issue. You see this equation 3 on the top. Can I write this as a rho upon rho v naught is equal to e to the power minus of t by tr?
Uh,
Yes or no?
but yes,
Now, if I
yes,
put
sir.
e is equal to tr, then I will write this as 1 by e.
Yes,
Then I can write rho v is equal to, that is the volume charge density is equal to rho v naught by e, or rho v naught times 1 by
yes.
e. Yes or no?
Uh,
This
yes.
rho v naught is very clearly written. This rho v naught is the initial charge density at t is equal to 0. This is what,
Charge density.
yeah, this is what you are asking
Okay.
for. What is the meaning of initial value? Initial value means there is some initial
Mm.
value at t is equal to 0. This value. And at t
Okay.
is equal to tr, at t is equal to tr, this final rho v is the 37% of this rho v naught.
Okay.
Now your confusion is
Okay, sir.
still any confusion. Then again I will explain. If still any doubt, I will.
No, sir, I got it.
So
No, no.
yeah, yes,
Yes, sir.
that doubt is clear. Hello.
Yes, sir.
So that confusion, that doubt is clear.
Hello?
Yeah. Hello.
Hello?
Hello.
Yes, sir.
So that confusion.
Hello?
Hello. That confusion is clear.
Hello?
Hello.
Yes, yes.
Am I audible to you?
Hello?
Am I audible to you?
Yes, sir. Yes, sir. Hello?
Yes.
Can you hear me, sir?
Yes. Am I audible to you?
Hello? Yes, sir.
Now your doubt is clear.
Yes, sir.
Yes. Okay. One more thing. Actually, my that class which was supposed to be from 10:15 has been cancelled. Actually, I got the call for that only at that time, 10 minutes back. So can we continue the
Okay.
class?
Yes, sir.
Yes. So better it would be better if we can continue because that has been cancelled. The candidate is having
Yes.
some exam, some school level exam. So
Okay.
he would not be able to come.
Okay.
So it would be better if we finish some more topics today itself. Okay.
Okay. Hmm.
So any other important commitment from your side right now?
No, sir.
So now we will see the another very important term, that is the boundary conditions. And in GET, usually they ask one or two questions from the boundary conditions. So
Okay.
yes, so also keep noting the things with especially those topics which I am saying, that because I am saying on the some analysis of the last
Hmm.
10 20 years after going through the problems and question papers. Okay, so this is what I
Hmm.
am. So means the purpose of highlighting this is that while solving the problem, means take a special care of these topics. Other topics need to
Hmm.
be taken care of because they are interrelated. But take a special care that okay, how to deal with the problem of boundary condition, how to deal with the problem of the coordinate systems. So take the special care of those. Okay.
Okay.
Bound,
Okay.
yeah, means all in all respect, either the problem solving respect or the theoretical aspect, in all respect, take care of the special care of these things. Go for the more
Okay, sir.
practice, more revision for these topics. Okay.
Okay.
So the boundary conditions, we will see that what the result says and what the theory says just right now. So see, if the field exists in a region consisting of the two different media. So what I mean to say by the two different media, let me just give you a very straightaway picture. So see, this is a interface. So see,
Hmm.
if this interface is something like this, just means I can, what do you mean? I mean by the interface or the boundary. Means above this, I can have a permittivity something like epsilon 1, and below this I can
Hmm.
have a permittivity like epsilon 2.
Hmm.
And suppose there is a object or surface placed like this. You see, it is sharing the both the media, up
Hmm.
and down. It is sharing
Hmm.
both the media. So in such case, what would be the relation between the electrical field component, the current density component, flux density component? This is what the boundary condition says. Okay.
Okay.
Then you can say what could be the possible varieties of the boundary separation. So one thing is that as I have drawn, this is the epsilon 1 or epsilon r1, epsilon r2. Another, it can be possible that up one is a conductor, down one is a dielectric, or this is conductor dielectric. Means the two media can be, one can be conductor, another can be dielectric.
Okay.
And the third is, of course, this can be conductor and another can be a free space.
Mm.
You see here. So,
Mm.
yeah. So from here, we have to understand the things. See the things here that we will consider the boundary condition at an interface separating the dielectric. Either it can be the two dielectrics with the relative dielectric constant R1 R2 as I had drawn the figure. It can be a
Mm.
conductor and a dielectric. And the last one is that it can be a conductor and a free space.
Free space. Mm.
Okay. So
Yes, sir.
yes. So we will see first. We will go for the derivation of the first. First we will go for the derivation of the this means derivation in the terms of the electric field and this. You see, we have studied. We will start from here. We have studied that for a electrostatic field, not always, but we are talking about electrostatic field. Its line integral over a closed path is 0. And I told you that if this is the case, then using the Stokes theorem, we can say that del cross E is 0 means electrostatic field is always conservative or irrotational in nature.
Rotation. Mm.
Yes.
Mm. Yes, sir.
First equation which we will use for the boundary condition is that integral of the electric field over a closed path is 0. E dot dl over a closed path. You can see this circle over a closed path is equal to 0. Yes?
Yes.
Yes. Means this equation means that electrostatic field is always conservative in nature or irrotational in nature. Yes or no?
Yes, sir.
Yes. Then another equation from the Gauss law, we find that surface integral of the this flux density is equal to net charge enclosed within the surface. Yes or no? Hello?
Yes, sir.
Yes.
Yes, sir.
So by the Gauss law,
Hello.
yes, hello. By the
Yes.
Gauss law, the surface integral of the flux density
No.
is always Q enclosed. This is the Gauss law. This is though it is
Don't
not
ask. Mm.
mentioned here,
Yes.
it is nothing but the Gauss law.
Mm.
Mathematical form of Gauss law, not the integral and differential, but this is the general mathematical form of Gauss law. Yes,
Yes, sir.
with the Maxwell's first equation also. Am I clear?
Yes,
So
sir.
yeah, so now we will use this. You know, it is I have not used it. I have stated it. So now you see the clear picture of the here, which I was also trying to draw, but I draw it very roughly. Here it is a very clear picture. You see. Consider the electric field E existing in a region consisting of the two different dielectrics characterized by, as I told you, that upper one can be epsilon 1 and downward can be epsilon 2. So epsilon 1 has been given as epsilon naught epsilon R1. We know that I asked you that relation and
Mm.
you told that
Yes, sir.
yes. And epsilon 2 is epsilon naught times epsilon naught R2. Yes?
Yes. Yes, sir.
Yes. So now you see here, this is the one block placed like this, and we have to find the electric field. You see, electric field E1. E1 is will be the having the two components. One will be a tangential T, tangential component. Another will be the normal component. I hope you understand these two terms, tangential and normal. Okay.
Yes, sir.
Similarly, E2 will have the two components, tangential component and normal component. You can see the vector diagram here. E given like this, one component is the tangential, and the normal, so it is the sum of this according to the vector sum. This plus this will give you this. Okay.
Mm.
Here also, this plus this will give you this. No problem?
Mm. No, sir.
No. So this is the general idea, but very important point comes here, that line integral over a closed path is always 0. Okay,
Okay.
I will use
Hmm.
this. How to use this? See, just very quickly, because derivation is not that much important from the get point of view, but concept is very, very important. As it is saying that even T delta of the W. So see the figure, delta of the W, this is my delta of the W means length part. So along this length there will be the tangential component. So E dot dl. So dl will be delta of W. So even T delta of W minus even N delta of H. You see the delta of H. Now the very surprisingly about the delta of H is that the half of this is above and half of this is below.
Hmm.
Yes or no?
Yes.
Yes. So half of this is above, half of this is below. So we are writing the even n times delta of h by 2, and similarly e2n times delta of h by 2 and minus of e2t delta of w, and again you will be having the delta of h by 2 and delta of h by 2 e2n and even n. So one thing you should only understand here is that to the sum terms we are writing plus. Sorry, to the sum terms we are writing the plus, and to the sum terms
Hmm.
we are writing, yeah. Sorry, this one 32. To the sum terms we are writing the plus. To the sum terms we are writing the minus. Can you tell me why and how? Seeing the figure, that answer is in the figure. Can you have a look at the figure?
Uh, Means because even and um,
Sorry.
no sir.
See, actually, you are not. I think you are not catching the one point. You are not noticing one point. The direction of the current. You see, for this part, for D to A, this is upward, and for B to C, it is downward.
Okay. Hmm.
Can you see?
Yes sir.
Yes. And similarly, for A to B, this is in this. Suppose I call this as a forward direction. Then C to D, it is in the backward direction.
Hmm.
So of course, one term will be positive, another
Hmm.
will go to negative.
Okay.
So this is how this equation has been written. Is it clear?
Hmm. Yes sir.
And this we have equated to the 0. So after equating to 0 and taking that, we are supposing that since delta h is a small quantity, delta h tending to 0, now we get the very, very important relation. And this one is the very useful for you. This you should know. The questions are asked on this, that tangential component of electric field. Listen my words very carefully. Tangential
Hmm.
component, not entire electric field. Tangential component of electric field is continuous. Continuous means if there are two boundaries, then it is E1 2 is equal to E2T, E2T. If it is E3, then E1T is equal to E2T is equal to E3T. So the is always tangential component of electric field is always continuous at the boundaries separating the two dielectrics.
Okay.
Are you getting my point?
Yes.
Here, without asking you, I will repeat once again, because here the very key point is there, which the sometimes mostly the students used to miss. The at the if you recall the figure once again, I will go back to the previous slides. This we are discussing one of the very important topic. That if you see this figure very carefully, this is the boundary separating the two dielectrics given by epsilon 1 and epsilon 2, and then at the boundary the electric field, the tangential component of the electric field is always continuous, which means that E1 is of t is equal to E2 of t.
Hmm.
Am I clear?
Yes sir.
then we know that D is equal to epsilon times E. Yes.
Yes.
So E will be D upon epsilon. E will be D upon epsilon.
Yes. Yes.
So of course, so if E1 will be D1 upon epsilon 1, D1 T upon epsilon 1,
Hello.
yes or no?
D1. D1. Yes.
And
Yes, sir.
E2T can be replaced with D2T upon epsilon 2.
Yes.
Yeah. Again, that this equation can be rewritten like this: d1 t upon epsilon 1 is equal to d2 t upon epsilon 2. So tangential component of flux
Okay.
density is also continuous, but thing is that not d1 t is equal to d2 t, rather d1 t upon epsilon 1 is equal to d2 t upon epsilon 2.
Hello. Two. Hmm.
I hope I am clear. If in doubt, you may ask.
Yes, sir.
A very important and a very significant topic is beyond told,
Yes, sir.
to ask anything. Once it is skipped, it is skipped, and we are don't having the time to go through the revision once again. We will discussing the
Uh,
question, there the revision will be there, but beyond toes and ask anything you are having.
and no, sir, I understood.
So, so remember this is that they are having the even t is equal to e2t and d1 t upon epsilon 1 is equal to d2 t upon epsilon t.
Goodbye. Listen to.
See, the very important point, as it looks like the continuous, but see the very important point. Sometimes in theory they may twist the question and they may ask in their own way that dt undergoes some change across the surface. There is some change, this word, some change, and what is that change? That change is that it is being divided by epsilon 1 or epsilon. It is being divided by epsilon 1 or epsilon 2. So it goes to some change across the surface, and that is why it is discontinuous across the surface. So
Okay.
sometimes something like true false can be framed that the which are which one of them is the true, that is the tangential component of electric field is continuous, tangential component of flux density is continuous. No, tangential component of flux density is not continuous. But yes, solving it is d1 t upon epsilon 1 is equal to d2 t upon epsilon 2. But theory and conceptually, it is discontinuous at the boundary. D means flux density. Electric flux density
Okay.
is discontinuous at the boundary. This is not continuous. Am I clear?
Yes, sir.
Okay. Then we will talk about the normal component. We talked about the this tangential
Tangential.
component. Now we will talk about the normal component. Normal component, for the normal component, we have taken a surface like this because the normal component needs to be dealt with the surface integral. So we'll take a surface like this, and here we find that this very important result, that this, see again, this normal component is also discontinuous because the d1n minus d2n is equal to rho s, not rho v, rho s. See, this is this normal component.
Okay.
D1n is minus D2n is equal to rho s.
Uh,
But suppose that if the boundary is a charge free region, for a charge free region, what will be the value of rho s?
mm.
For a charge free region, what will be the value of
0.
0? Again, now there's a very important conclusion.
0.
For a charge free region, this is continuous. Because now d1 n is equal to
Okay.
n, but very strictly for a charge free reason. But the general case which we were discussing, that was a dielectric case, for that d1 n minus d2 n is equal to rho s. So for the two media, this is the conclusion. If I put in the one or two line, for the media separating the two boundary, the tangential component is always continuous, but the normal component, that is the d1n and d2n, are continuous for the charge free region only. Am I clear?
Okay. Yes, sir.
Yes. I will share the link of the recordings, but for the time being, you just understand at least the basic, because I am doing so much of the
Okay.
effort, I am giving you so much of the hard effort. So at least take away something after the class.
Okay.
Okay. Is it clear?
Yes, sir.
Okay, so this electrostats is almost clear. Before going to the
Mm.
magnetostats, I would like to take one more class, the next class, to discuss the few problems asked in the last 5-10 years. So better we will stop
Okay,
here,
sir.
because there is no meaning
Okay.
going for theory and theory. That is not our goal. You have joined the class
Okay.
for some purpose, that you should be able to understand and solve at least the some questions in the MFT in the gate. So
Yes, sir.
will be unaccomplished if we don't go through at least the problems which have been asked. You get never
Yes, sir.
repeat, but at least the pattern we should understand that how to analyze the problem. As I have shown you in the previous
Okay.
lecture, that some problems related to the coordinate, curl, divergence, I had already discussed it. Yes, no?
Yes, sir. Yes.
Likewise, I would like to discuss at least 7, 8, 10 problems which have been asked in the last few years related to the Gauss law, related to the differential integral form of the Gauss law, related to boundary condition, related to electrostatic potential. Then things will become clear that yes, what we have studied, how
Okay.
we are applying. So we will stop
Yes, sir.
here. Theory part is okay.
Yes, sir.
Part is over. We'll go through the theory part. The next class I will see. Hopefully now I think it would be possible on Saturday only. So Saturday, Sunday again
Oh,
I will go for the class, and we will
okay, sir.
electrostats, and also we will try to start the magnetostats at the same time.
Okay, sir.
Okay. So,
Okay, sir.
so how far it is going till now? Means what is your means how far it is meeting your expectation? Because time to time we
Yes, sir.
interact
It's good.
the
Actually, this is the first time I'm understanding something in electromagnetic.
sorry.
This is the first time actually I'm studying electromagnetics since college. It was just mugging up those derivations. Just
So now you are able to grasp the things at least to some extent.
yes, sir.
A very vast subject. No, means in a very less time, nobody can put like a capsule thing like to can provide a capsule thing like to any student. But at least I'm trying my level best to make it as simple as possible, to make the cognizance as simpler as possible. So just
Yes, sir.
between we should get the some feedback also that what is going, or if it is not up to the satisfactory level, then of course we can go for the some modification, some modulation there. So that is what my basic aim is, to ask that. Always I keep on asking that. So if anything related to that, you may share that, sir, this is going this way, or you may go like this way, then it would be better. You may put your suggestions, then we can incorporate that. Okay.
Yes, sir.
Okay. So, okay. Have a good time. Next, I will inform you. If possible, I will try to take a class on Friday, but since it is a bit hectic on Friday, so hopefully it will go on.
Yes.
I will inform as I informed today.
Okay, sir.
Okay, thank you.
Okay, sir.